Swayam Prabha. Digital India. Educated India.
Welcome to this talk about heat transport at the nanoscale. And heat transport is a perennial, ubiquitous phenomena. You see it everywhere, and when you were young, you might remember something like this: watch out, the cold will go out. Leave the fridge door open. Heat has to be managed there so that the refrigerator continues to cool. There are many other situations, especially in the northern countries. Insulated homes are very important to protect them from extreme environments, and that could require the heat to stay out, thermal insulation. Materials whose thermal properties or heat flow is adjusted so that they don't transport the heat between the two regions, the region inside the home and the region outside the home. And then something you're all familiar with, because now you are in 11th standard, most of you may be having a mobile phone which often gets heated up, and this is an opposite scenario where you are required to dissipate the heat rapidly, opposite of what you wanted here. Here you want to keep the heat out, you need a thermal insulator. Here you need a good thermal conductor, so it should pull out the heat before the electronics or the core part, the chips inside your mobile phone, get damaged. Then this is because you're all the young generation who's going to be the future of mankind, playing an important role there. So you should think about how green is digital. I'll give you the context of heat here also, but for the moment think about this. So much of energy is invested in storing data. This is only for the United States. Across different states as of now, these are the states where 15 to 20% or even more of the electricity is used just to store data. That's enormous because US is one of the biggest consumers of energy, and this might give some more idea. All of you are familiar with YouTube videos. There are in hundreds, thousands, millions. How many? Some estimate was done last year or 2 years back, and they found about 10 billion videos were uploaded within 1 year, and all of it is free. So where is that energy cost associated with? Of course, if you compare paper with equal amount of digital storage, then digital storage is better. But if there is unlimited digital storage, then there is an energy cost, and that cost could be enormous. So there are these data centers where heat management is a problem at all scales. You can see steam rising out of these data centers where so many billions of videos are getting stored, and not only at the level of the entire data center, but at the level of the chip also the heat has to be extracted. Whether it is at the data center or a single PC, this is a continuous problem that one needs good materials with good thermal interface, good thermal conductivity, which can pull out the heat from the system and prevent the electronics from getting damaged. So all this to show that thermal management or heat management is a big challenge today, as it was also earlier. And in this talk, we look at the science behind this. And since this talk is specially curated for high school, so I think I'll begin with a very simple concept. Can we understand heat transport in gases? Because they are the simplest systems, and if we can understand, can we use that to build upon that and try and understand what are the complexities of heat transport in solids? What describes the heat transport in gases is this kinetic theory. You can assume the gas molecules are in random motion, and more the temperature, more energetic they are. That doesn't seem like a very big assumption. You heat up the gas molecules are going to possess more energy, and statistical mechanics tells us that for each degree of freedom, because these gas molecules are free, they can go in the x, y, z direction. For each degree of freedom, there is a half kT or something proportional to the absolute temperature multiplied by the Boltzmann constant, and there are 3 directions. So it's 3 into half kT, it is 3 by 2 kT. That's the average energy that the gas molecule possesses. And if the temperature is higher, they possess proportionately higher energy. So these are the gas molecules in random motion, but we are not dealing with one molecule, like I have shown there, 3 by 2 kT, but there could be n number of molecules. Well, n is like an Avogadro number. So there are, say, 10 to the 23 molecules, and the energy possessed by them is 3 by 2 n kT. More the number of molecules, more the total energy they possess. But this suggests if I have to raise the temperature of this gas by 1 degree, that is, I change the T by 1 degree, or I set T equal to 1, delta T equal to 1, then the heat energy required to do that, to raise the temperature of this gas, is 3 by 2 n kB. The T has gone because I have set T equal to 1. So how much heat energy is required to raise the temperature of the gas by 1 degree is this quantity, which we call as the heat capacity. These are familiar problems when you are making tea. How long I should heat, how much heat should be provided, and we can break it down and say how much heat to be provided to raise the temperature of the water by 1 degree. Nobody makes tea that precisely, but as a mathematical question we can ask that. And then one should throw back the question, you didn't tell us how much water is there. So tell us how much water is there, then I can say how much heat should be provided. So instead of working with heat capacity, which doesn't give reference to how much material is there, you can work with specific heat, which for water is 4.184 joule. That is the amount of heat you need to give to 1 gram to raise the temperature by 1 degree C. Then what else can happen? You can fill a balloon. Since we are still sticking with gases, we have not yet gone to solid, you can fill a balloon with gas molecules and you can heat it. Well, don't try this because most likely the balloon will burst, but not on this picture. I can sketch anything. So what will happen is that this gas can expand. So apart from getting heated, it can also undergo a change in volume. But we are only interested in the effect of raising the temperature, not the change in volume, because now the gas is doing some work, it is expanding. So let's say the volume is kept fixed. We don't want the volume to change. So we talk of this specific heat at constant volume. And this is the quantity which is independent of temperature, which is what we have estimated as 3 by 2 n kB. If you increase the number, okay, we can also divide it by n if it's specific. Otherwise, if it's total, we have to multiply it by n. So then how do gases conduct heat? Does the idea of heat capacity or specific heat tell us something? If the gas is put between two boundaries which are at a temperature T and they are undergoing random motion, then there is no conduction because there is no temperature difference. So they are still undergoing some motion. To have conduction from one place to another, there has to be a temperature gradient. There has to be a hot side and there has to be a cold side. And the heat can flow from hot to cold. Cold doesn't flow from, as I showed in the first picture, cold is never flowing, it's the heat which is flowing. And microscopically we can think these red ones are the energetic molecules or atoms of gas. They possess more energy, and when they undergo collisions, they will transfer the energy to the other side. And at the end, there will be what we say equilibration, that the entire gas will have the same energy. At the same time, there is no net particle transfer. It's not that the hot molecules just came to the cold side. No, they underwent collisions. They transferred the energy through many, many collisions. And at the end, the temperature is common for the whole thing. There is no net transfer. Although the particles move from left to right, they also move from right to left. At the end of it, the particles are just preserved at any volume that you take inside. Now, one quantity which now we can arrive at, because we are interested in heat flow, is the thermal conductivity. And I will introduce that in many different ways. The thermal conductivity is a measure of how good the heat is flowing. More the thermal conductivity, it's flowing faster. Less the thermal conductivity, it is flowing slower. And intuitively, though we can do a derivation, if you take up a physics course in your college, you might do that, but it is proportional to these three things: specific heat, which I just introduced, and the mean velocity of these molecules, and the mean free path of these molecules. So let's see what these three things are and why we believe it should be proportional to them. Specific heat is how much energy you need to provide to raise the temperature. That's what I just introduced. So if it's a measure of how much heat energy they are storing, when we are saying there is a temperature difference, the hotter side, is it storing more energy? It would be storing more energy if the specific heat was higher. So that explains the proportionality on C. Then it's about heat flow. If the molecules are moving very rapidly, they are transferring the heat more effectively. They require less time to reach the other end. So heat flow is faster if mean velocity is faster. And then there is mean free path, which may be a less intuitive quantity. It is the distance they travel before they undergo a collision. So if they can travel, let's say, from this end to very close to the other end, they are transferring that energy more effectively because they are reaching closer to the cold end and then transferring the energy. On the other hand, if they just strike a molecule nearby, then they are not traveling that much in distance before they are transferring. So energy transfer is more efficient if the mean free path is longer. And it's not a proof, but it's just an intuitive idea that you can multiply these three and K will be proportional to that. Yeah.
Again, when you talk about mean velocity, if that is more, then essentially heat is flowing faster.
No, it's not. It's not enough to talk of mean velocity because you may have high velocity, but it doesn't tell you how many other molecules are present around you. The mean free path factors how many other molecules are present. If you do an exact calculation, which is fairly tedious, you'll get the same result with a factor of 1/3. You can think of an analogy. I mean, people who did not follow the previous discussion can look at this one. So you can think of these molecules like billiard balls, and the heaviness of the ball is like specific heat because that is possessing more heat energy. So that's like heavy thing, it can transfer more things. And the strength of the strike is like the mean velocity. You can strike gently, you can strike hard, so that's the mean velocity. But that's not the complete picture. I need to factor what are all the other billiard balls, where they are placed, are they all bunched together, are they there at all? All these questions can be asked, and that defines your mean free path. The first two are easy because we have already found the specific heat and you know how we will strike them and what velocity they'll achieve, what temperature you will provide, what velocity they'll achieve. But mean free path is little difficult to find. You need to factor all of the others. So then we are done with gases, and let's extend this idea to solids. We are interested to know how heat flows in solids. How the mean free path is calculated. Mean free path, I am not showing the calculation, I am just introducing this quantity. It is the average distance, mean free path before it has a collision. The distance it travels before it has a collision. If it travels more distance before a collision, it is transferring energy over a bigger distance. So heat flow is more effective. If it's only traveling a short distance, so it will come up again and again, but I think for this. How exactly? Yeah, it will come again and again. Maybe at the next. So this is a preliminary introduction. Yes, please. Right. No, that 1/3 is there's no physical significance. And for the purpose of this school level talk, I think the intuitive introduction is sufficient. If you ask me for the more elaborate discussion, it is typically done for the MSc course, where we start with Boltzmann-Transport equation and derive out maybe in 1 or 2 lectures. If time permits, at the end I can tell you a little bit about Boltzmann-Transport. If any other teacher has discussed that, please let me know. So far? No. Okay. So if you have time at the end, I can please remember. So let's extend this idea to solids. And again, I'm starting with something very simple. V is equal to IR. All of you know that you apply a voltage, a current flows, and how much current flow depends on resistance. So this pictorial depiction of this idea, which I found on the internet, is a very nice one. The voltage is trying to push the current. Hey, go more, right? And the resistance is trying to squeeze it. We don't want you to go. So this is the balance, which is V is equal to IR. And you can extend this idea to heat flow by making appropriate changes. It's the same concept, the flow of current and the flow of heat. And what are the changes you will make? Instead of voltage, now you have temperature gradient or temperature difference, hot side, cold side. Positive voltage, negative voltage replaced by hot side, cold side. That is the driving force. And the electrical current is now replaced by the heat current, the flow of the heat energy instead of electrical energy. And what is trying to stop that is thermal resistance. What is it? We don't know. But maybe intuitively you can say thermal resistance, okay, electrical resistance comes from electrons getting scattered. So thermal resistance may come from heat getting scattered. And for the rest of this lecture, I will prefer thermal conductivity over thermal resistivity or resistance. As you know, they are inverse quantities. Thermal resistance is a measure of how much they are stopping the heat flow. Thermal conductivity is how much it is allowing the heat flow. So it's in inverse dependence, and there's also a geometrical factor between conductivity and conductance, as you're already familiar with. Right? A different approach, because this is how we are pedagogically building the topic, but historically people came to thermal conductivity from a different route. The first thing they discovered, they didn't say let's study gases, now we'll study liquid, then we'll study solid. That's what we are doing today. But they said there are these interesting solids, and if you make a bar out of that and you place one end of the bar hot, other end of the bar cold, heat will flow. And that flow will depend on how much is the temperature gradient. 100 degrees dropping over 1 meter, more heat flow. 10 degrees dropping over 1 meter, less heat flow. It's a direct proportionality. And that's an empirical result. Now we can rationalize it through theory also. But originally it's discovered empirically. It's proportional to the temperature gradient. And this is the amount of heat that is flowing across some area. Area can be brought in here also. You can talk of heat flux is proportional to temperature gradient, and that proportionality constant is called the thermal conductivity. And there can be many other geometries. Heat will always not flow in one direction. Yeah.
Is there any analogy with viscosity with previous equation?
Yeah, eta A. So you are looking at yes, there is some analogy, but how far we can extend that, we'll have to think about it. I mean, mathematically there is an analogy, that is correct. Because here also there is something resisting it, but here thermal conductivity is actually not like viscosity. It's the opposite of it. Because that's a viscous force that is resisting it, and here it's the heat flowing. So in a sense they are doing opposite things, but there is some mathematical similarity. There can be other geometries. You can have, say, a laser shining on a surface, and that will produce a disk which is heated, and that heat will flow outward radially everywhere, like I have shown here. Now I cannot use delta T by delta X because heat is flowing radially outward, and that brings the concept you might have studied, some of you might have studied, the gradient. Because there is a temperature constant surface which is a circle, and the vector which is normal to that surface is the gradient. So you have gradient of T, and the heat flux, which is a local heat flux density, watt per meter square, is proportional to the gradient of the temperature, and the proportionality constant is thermal conductivity. Thermal conductivity, then if you look at this equation or the previous equation, it has units of watt per meter Kelvin. Engineers do this, yeah. Right.
What determines the geometries of the
What is the?
what determines the geometries of the
I was just saying in this slide, you can, so the previous one was just a linear geometry. So you can talk of delta t by delta x, where x is this dimension I have drawn here, linear dimension. Temperature drops from here to here, there is a bar, this end is at 100, other end is at 0, right? But here it's a circular geometry. The center part has been heated. Heat is flowing radially outward. We need to describe this and all possible geometries. So this is more generalized version of the law. If you want to write a law valid in all geometries, you will write this. That's a simpler one. The previous one is just easy to write, easy to understand. Engineers like this, and I think when I looked at the list of lectures, there was a talk on heat equation. Probably it has already happened, I'm not sure. Yes?
Spoke about wave equations.
Wave equation. Right. So then, if you take this Fourier's law, which I have introduced many times, that heat flow is proportional to the temperature gradient. More the difference, more the heat flow. You combine that with energy conservation. Energy is neither created nor destroyed, everything is conserved. Put together will come to heat equation. And heat equation is interesting when you are working with different geometries. You want to know, engineers want to know, I have this very complicated design, what will be the temperature distribution as a function of position and time. Some equations, though I don't intend to spend time on this because it will take away time from more interesting things I want to discuss. So this is Fourier's law. You can write some energy conservation and it will bring you to heat equation. Essentially U is same as T. I should have used the same symbol. The U is the temperature. So solving this differential equation, which is a parabolic differential equation, will tell us the solution U, which is temperature, capital T, as a function of position x and time t. We are not interested in this. We are interested in only this quantity, K. We are not interested in the heat equation. Heat equation is macroscopic, universal. All situations are handled. Maybe the solution of differential equation is difficult in some situations. You can do it numerically, you can do analytically depending on the situation. So here is the interesting puzzle, why K is so interesting for physicists. Take this structure. This is the structure of gallium arsenide, a semiconductor that you may be aware of. And these are the positions of atoms if we take one repeating cell of that. One is gallium. The color differences are there, maybe not so apparent to you. So the brown and purple are the colors. So one atom is gallium, the next one is arsenide, then gallium, and so on. And instead of that, if it were diamond, the atom positions are identical, except all are carbon. Right? Diamond is an allotrope of carbon. So both have the same positions of atoms, but if you look at their thermal conductivity, diamond has very high thermal conductivity, one of the highest, 2290 watt per meter. And gallium arsenide has only 50 watt per meter. That means even if we know the atomic positions, we really don't know anything about how heat is flowing in the system, because here is an example of two materials, same structure, same positions of atoms. One is very good heat conductor, diamond, and other is very poor heat conductor, gallium arsenide. And these are the type of questions we are interested in as we go along. So whatever we learnt about gases, if we extend that to solids, we will say the following. Now the atom is not, or atom or molecule in the gas case, is not free to move in the entire space, but it is sitting in a cage of its neighbors. The neighbors are not allowing it to go anywhere it likes. Stay within this boundary, just like you are sitting on these tables, benches, chairs. You are not allowed to go around, right, unless it is 10 o'clock. So then they possess a kinetic energy because they can still move, but they also possess potential energy which the gas molecules did not possess. That potential energy comes from these springs, which are the chemical bonds. The gas molecules did not have bonds between them. The solid atoms have bonds between them, and they are like a spring. The spring also possesses energy, and so counting the total energy, it will be kinetic plus potential. And if you think of it like spring mass system or an oscillating pendulum, then half the energy is sitting with kinetic, half with potential. One can derive it, but we also have a feeling for it. Yes, the energy keeps transferring between completely potential to completely kinetic, and then we take an average, maybe both should be equal. So if we take both to be equal, then the specific or the heat capacity here, because I have still the n there, the heat capacity is 3n kb instead of 3 by 2n kb. I have added 3 by 2 for the gas result, and then to that I have added 3 by 2 for the potential energy. Both are equal, so it becomes 3n kb. And this result historically was found by Dulong and Petit, and it's called the Dulong-Petit Law. It works so well. There are these so many elements sitting here, and the scale is 23 to 29. That's some kind of window of error. It's not 0 to 30. So you can see all the numbers are bunched around this value. This is in molar units, so it's gas constant 3R, but it's same as saying 3 times kb or 3 times n kb, depending on the units that you're using. So this was a very empirically successful law. They were able to explain the heat capacity of solids. And can we build upon that? Because we know the theory behind the thermal conductivity of gases. So with this clue, can we come to thermal conductivity of solids? This is the reason to show this. I hope it is clear. So let's put a tick mark. C is for gases and solids is almost the same. There is a factor of 2 because solid also have potential energy. But we understand that. And then if we can also write the expressions for mean velocity. But where is the velocity? Those are trapped in the cages. They are not moving. And mean free path, what is moving there? There is no mean free path. The atoms are fixed. So we are still struggling what to do with V and L. But we have fixed C. Any suggestions? What should I do for V? If I am using the same theory, I am learning from gases and extending it to solids, what should I put for V? V of what? Of what? Huh? Molecules? But they aren't moving, so what? Vibrational energy. See, you are many centuries ahead of time. So when people first thought about this, they were not aware of the atoms at all. They didn't even know about the vibrations. First the atoms should be known, then vibrations should be known. But what they did know was about current. This current was discovered long back. Michael Faraday discovered ideas about electricity and so on. Atomic structure came only after quantum mechanics. So when they knew about current, they thought, why not the electrons are also carrying the heat? Electrons, they had some idea, some particle is carrying current. They is carrying charge. Can it be that is also carrying the heat? So then this could be the velocity of those electrons, and L could be the distance the electrons travel before they scatter. Thinking very classically, Newtonian way, electron is some particle just moving around like a billiard ball and getting scattered. That's not actually true, because there are many ways of transferring, and it's not moving around like a gas particle. Energy is transferred, whether it is electron or it is vibration. Energy is transferred from one atom in the solid to another through the bonds. The bonds are the crucial thing. It's not the free motion. And analogy, or just to break the monotony of the discussion, gases can be thought of a street where people are just floating around, bumping into each other, and there is no order. And solids can be thought of like this game of passing the parcel. You are passing around the heat in a very neat manner. So essentially the phenomena diverge at this point. When you can't use all the ideas. Specific heat or heat capacity works well, but after that we have to look at specifics, and these two are very different phenomena. This is the heat transferred like electrons, but could also be transferred like vibrations. So I asked what particle can carry the heat, and it was the electron, as people originally thought in 1850s, because they didn't know about any other particle, and it was carrying current and heat. And K, the thermal conductivity, is proportional to electrical conductivity. That is, how effectively it can carry current, same effectiveness it has to carry the heat. It was found that it is correct for metals. If a metal carries current, electrical current nicely, then it also carries heat equally nicely. And we can understand that because whatever scatters the electron scatters the heat. Electron is the carrier of heat. We don't know what scatters it, but when it moves in the solid, something is scattering it. The same thing is scattering the heat. So K is proportional to sigma. K is equal to LT sigma. L is the Lorentz constant. And this was the Wiedemann-Franz Law of 1850s, and whose success you can see with this diagram. If everything is not visible, I can just read it out. This is thermal conductivity, this is electrical conductivity. And here are bunch of systems, metals and metal alloys, like this is stainless steel, and this is zinc alloy, copper alloy, and so on. Tin is here. So it shows good electrical conductor is good thermal conductor, poor electrical conductor is poor thermal conductor. It's a linear relationship. But there are exceptions, and that was one big trouble. There are materials like diamond, which are electrical insulators, very large band gap in diamond. So, but it's one of the best thermal conductors. So then it is sitting out here, completely violating the Wiedemann-Franz law, which means this is not the complete picture. There are systems where electrons are not carrying the heat, something else, and we need to discover what that is. That was one objection. There was one more objection, and this I am following the history of heat transport. It came from the free electron theory. We counted the specific heat and we found the Dulong-Petit Law is correct. 3 nkb is true for all solids. But then we forgot about the electron. That is just the atom, that's the nucleus, which is connected with bonds and it's moving around the equilibrium position, but there are free electrons. They can move the way they like free gas molecules. So they should also possess, each should possess a 3/2k for its kinetic energy. And put together, then the heat capacity should not be what we found, it should be higher. And that mystery deepens because electron, if it is carrying, we have some explanation, like we saw the Wiedemann-Franz law. But then if electron is carrying, we didn't even account it in the specific heat, and there is some contradiction, some paradox sitting here. Electron does the job, doesn't do the job, does it for thermal conductivity, doesn't do it for heat capacity, and so on. What is the? Small n is the number of free electrons for each atom. So the puzzle was solved later with quantum mechanics. You can think of the electrons like occupying a sea, and you can give the energy to only those which are at the surface, because they can take the energy and go into the boat or wherever they want to. But those which are deep inside the sea, that is at lower energies, if they take the energy, they'll go to the neighbor. But Pauli will say, don't do that. Not allowed. So they can't take the energy. So only a very small fraction of electrons can take the energy. And going back to the previous result, this contribution is not there and nothing is wrong. Everything is accounted for. I hope this is clear. So C is just of the lattice, which is 3 nkb, and the C of electron is very small. Then people obtained the data for lower temperatures. I am not showing the graph, but they found this heat capacity, which is 3 nkb at room temperature for all materials. If you cool them down, the heat capacity starts to decrease lower and lower, tends to 0 at low temperature. But that is not explained by whatever theory we have considered. Yeah.
So, why don't you mention liquid,
Because of the limitation of time, I have touched upon only gases as a motivation to come to solids. But in between, we can also have liquids, but just that we don't have enough time to go into that. You can think of it as an intermediate stage. The interactions are somewhat similar to solids, also somewhat similar to gases. It's the gases with more interaction, and the kind of liquid will decide how much interaction. Water has a lot of interaction, and some other van der Waal liquid will have very less interaction. So Einstein tried to explain this by saying that the vibrations are quantized. We think of vibrations as something continuous. Pull a string, it is vibrating. It has all possible continuous energies. But Einstein proposed that the energies have to be quantized to explain why heat capacity goes to zero. And the one thing he considered was, in his simple model, that the vibrations of one atom are not connected to vibration of the neighbor. They are all vibrating independently, independent oscillators. One atom is there, it is doing its vibration about the equilibrium point. Next atom is doing the same about the equilibrium point. With this model, he was able to explain many things.
How will they vibrate independently?
No, it is wrong. I mean, it is the first step. So I'm just explaining historically. He took it like people didn't know at that point. So he said, let it vibrate independently. He was able to explain that the heat capacity goes to zero as temperature goes to zero. But that wasn't correct, as you pointed out. Maybe you have some connection with Debye. Debye also came to the same conclusion after Einstein raised this point. So Debye said there is coupling between atoms. How can you say that the atoms are vibrating independently? Debye also said the same thing. So then if they are coupling, it's a very hard problem, because there are 10 raised to 23 atoms in a solid, let's say, and each of them has bond between each other. So there are 10 to the 23 or even more number of bonds. Each can have many bonds. With that large number of bonds, they are connected to each other. We have no idea how we can solve this problem. It's extremely hard. We want to know the coupled vibrations of all these atoms. How many equations we need to solve? At this juncture, Debye was able to picture that the atom vibrations are like lattice waves. You can break it down and think of a wave moving inside the solid, where all the atoms are moving in a periodic manner, like a traveling wave as depicted here. So this was his very important contribution, new concept. But let me come to things you are familiar with. You are all familiar with sound motion. Sound is also kind of a vibration, and sometimes it's just unavoidable. That's the unfortunate thing about sound. You can put walls, sound gets through that, because sound is conducted by gases, sound is conducted by solids. And in solids, we know this formula. I think you have studied in your school, right? So then the sound velocity is proportional to the square root of Young's modulus divided by the density. That means there are some microscopic parameters on which the sound velocity depends. It doesn't depend on the fine graining or knowing the atomic structure. If I know elastic property, how stretchable the solid is, what's the density of the solid, I can tell how fast the sound will move. In stainless steel, it moves 5 km per second. That's why we have heavy metal bands. They produce a lot of sound. Sound travels so fast in steel. Okay. Heat motion of that, just a light remark, not really. Huh? Okay. So heat motion of atoms and elastic waves in solids, there is a connection. This connection was proposed by Debye. Just like sound travels, and we know from the macroscopic picture treating it like a wave, the heat can also travel in a similar way. This is the idea proposed by Debye. But there is a difference. Sound waves, you are familiar, are in kilohertz. What's the range of sound? 20 to 20,000 hertz. But the heat waves, they can go all the way up from low values, from kilohertz, they can go all the way up to terahertz. So the molecules or atoms are vibrating very, very rapidly. And in that very rapid motion, they are transferring the heat from one neighbor to another neighbor. In sound, they are also transferring the energy, but sound is at very low frequency. And we can't hear all these heat waves. They are just going around. You can hear only the sound range, and most of it is, well, kilo is 10 to the 3, then mega 10 to the 6, giga 10 to the 9, tera is 10 to the 12, and that is the high frequency over which heat waves are moving. So here Debye was able to show that once this is quantized, if you decrease the temperature, all those terahertz modes, they cannot be excited because they are very high energy modes. Only the modes with low energy will be excited at low temperature, and specific heat will be proportional to cube of temperature, which was also the experimental observation. Now some analogy. You have come across electromagnetic waves, and they are oscillating electric magnetic fields, right? Electric field is perpendicular to magnetic field, and both are perpendicular to the direction of propagation, as shown. In later higher studies, you will see that these two pictures are not disconnected. We also think of light as a photon, a particle of light moving, as if we are firing bullets and the photons are going there. And then we are also thinking it is like a wave. The two pictures are unconnected, but in quantum field theory, you can make the connection. You can go from one to the other. That is, you can quantize this field to come to a photon. So the quantization of the electromagnetic field gives you the photon, which is a particle of electromagnetic radiation. Similarly, identical mathematics, no difference at all. Vibrations are also periodic, just like electric field, magnetic field are varying periodically. Vibrations are varying periodically. If you quantize them, you get one more particle. Well, you do the same maths, so you get something, you have to give it a name. So you call it phonon. And now you can think of solid like an empty box, just like vacuum, where you have put this phonon, quantized vibration, which is freely moving, as if the heat carrier will have infinite thermal conductivity. Because when you take vacuum, you take the electromagnetic radiation, it has filled up the space. You quantize, it's a photon, it's just traveling, nothing is scattering. Even the photons are not scattering each other. It's not that I mean, these are questions to think about. I am shining this laser. Why are the photons not hitting each other and just spreading away? Right? That's not happening.
That's because photons can only interact with the electrical charge. And photons themselves don't have electrical charge.
Photons can only interact things with electrical charge only. Photons can also interact with photons, as I will show you, but it's very weak, extremely weak. The same is not true for this, as we will see, phonons. So at some level they are very similar, but there is one fundamental difference which makes them very different. And you are also aware, if you pay attention to this picture, if you have read this book, The Calculus Affair, that light is so easy to control. You take a lens, put light, you can focus it, and try to focus sound, and there are like such complicated apparatus proposed in science fiction. Maybe some of it has been also realized today. So if sound is harder to study or understand compared to light, heat is much more harder to understand than all of this. And these are some simple pictures to convey the idea. Photon is just traveling in vacuum like a particle, nothing scatters it. Sound waves inside a solid are also scattered. You direct sound towards the wall, but people at the other end can also hear what is going on. So sound is easily scattered. Phonon, well, we have just quantized it. We have reasons to believe it should be similar to photon. We also have reasons to believe it should be similar to sound. And exactly what is happening, is it traveling freely with infinite thermal conductivity, or is it getting scattered, and why is it getting scattered, we don't know. So here are some things to think about. Electrons, easy to study because you can take a voltage source, you can inject electrons. People frequently say that inject electron, apply a voltage. Or you can use a multimeter, measure the electrons. You can measure single electrons also if you have a sophisticated instrument. And then you can control them with electric and magnetic fields. Photons, again, you have such very simple palm top or maybe bigger one, bench top sources, which all have one single wavelength. And you have spectrometers, and photons don't interact strongly with each other, so it's easy to study. But when you come to phonons, there is no source. You can't give me a source, say, produce phonon of this wavelength. Nobody can do that. It's impossible. And they don't interact with electric magnetic field. They don't have charge. But they strongly interact with each other. So it's a very hard system to understand compared to the previous two.
So wouldn't heating anything itself produce phonon?
But it will produce a spectrum of phonons. You can't produce a phonon of a given wavelength like you can produce light of a given wavelength. And these are some weird kind of scatterings which happen. So this is still normal scattering, so it is weird but not that weird. So I'll come to more weird in a while. Think of this as crest and trough. There is a wave going up and down, up and down. I only marked the position of crest and trough, high point, low point, high point, low point, and this is a wave. This wave is a vibration. It's a phonon coming from this side, another phonon carrying the heat coming from another side, that they have different wavelengths. And I've tried to show it geometrically. This is what happens. They can combine to create a new wavelength. And how this happens, new wavelength, is through these intersection points. I have drawn this new wave which is emerging. In terms of frequency, because frequency is inverse of the wavelength, at least for light or for sound. So then h bar omega 1 of the first wave plus h bar omega 2 of the second wave is adding up to give a new h bar omega of the third wave. For light, it doesn't happen, right? You don't take two red light and get a green light out of it. But see, it happens in phonons. But the good thing is, when phonons do this, they are still transporting the heat like they were doing. The heat transport direction did not change. Heat was transporting, say, along this direction. When they combined, the successor is this new particle, continues to carry the heat in the same direction. Heat transport not disrupted. Again, we are back to thermal conductivity is infinite. Phonons are scattering each other. Crystal is a perfect crystal, no defects. Thermal conductivity should be infinite. And this is, as I was saying, rare for light. But you can have this second harmonic generation where you can have two infrared photons combined to give a green photon, a completely different field. I'm not the person who should discuss this topic. There are other researchers working on optics and photonics, but these phenomena do happen. Very rare. So we are calling this normal process as N process in whatever follows. In N process, energy and momentum are given to the successor and heat flow is not affected. But there is the following property. If you put some defects in the solid, like these are isotope defects, the green portions are some isotopes. I hope you understand what is an isotope. So the isotopes have the property, the long wavelengths are not scattered, the long wavelength, but the short wavelengths are easily scattered, as I have shown here. So some thermal conductivity comes down, but what the N processes do is the following. Two long wavelengths can become a short wavelength, then they can get scattered. So a lot of scattering can happen indirectly due to the defects present in the system. And I'll take another maybe 5-7 minutes to conclude because we started a bit late. I hope, when is your next lecture? 10:05. Okay. Sorry? Yeah. Okay. So there are these U processes, a different kind of process, and this is extremely interesting. Nothing like this in the photons, nothing like this at all happens. Think of this vibration with atoms going up and down, represented with black, right? and the condition is that the wavelength is less than twice the atomic spacing. So you have this very rapid oscillation. That same rapid oscillation can also be expressed as a long wavelength vibration, shown with the red. There is an ambiguity. Two curves are passing through the same. Which is the vibration? We don't know. Is the black one the vibration or the red one the vibration? Both are passing through the same atomic position. A short wave moving to the right, as you can see with the faint one, so this is moving to the right, is equal to the long wave moving to the left. And this ambiguity never happens for photons. There is a fundamental reason. The fundamental reason is that the electromagnetic wave is defined at every point in space. We know the electric field, we don't know the magnetic field at all the r and t. But the vibrational wave is only defined at the atom. It's not defined in the intervening space. We are filling up as a mathematical entity, we are filling up the remaining vibration. So we can have a situation which is U process or Umklapp, German for flop over, that wave going to the left suddenly becomes a wave going to the right. And then what about the energy? So another analogy with this is, the wagon wheel effect. Wheel is rotating rapidly. You must have seen, then suddenly at some sampling rate it starts to appear as if it's turning the other. But here it is apparent. In the case of phonon, it is real. So analogy breaks down there. I just wanted to convey the idea. So N processes are transporting the heat, but U processes,
What we are telling is, at one point in time, the short wave moving to the right, but suddenly it becomes a long wave moving to the right.
right?
How do we distinguish when it is a short wave, when it is a long wave?
Yeah, so the condition I have given, lambda is less than 2a, is the condition when this flop over happens. When this ambiguity is there and flop over happens. So suppose two phonons combine, their energy will increase, the wavelength will decrease. When they combine, the energy will increase, frequency will increase, the wavelength will decrease, become less than 2a, then the flop over happens and the heat will flip in direction. So this is diagrammatically shown here. Two of them combine, they give a phonon in the opposite direction, and it's extremely puzzling how this can happen. Momentum conservation is violated, energy is not, but it looks like heat is going in the opposite direction, because momentum in a solid is very different from momentum conservation what you learn in your classical physics. And so we are doing experiments to measure thermal conductivity in our labs here. This will, because we have run out of time, I won't spend time here, that we use lasers to heat up materials, and we look at how the temperature changes, and we set up some models to explain what is the thermal conductivity, and we have obtained some interesting results, like you can take graphene, which is a honeycomb lattice of atoms, and we view that under a scanning tunneling microscope. We can occasionally find that they are rotated by some angle. It produces a very unique Moire pattern. Moire pattern is like take two layers one above the other, keep rotating them, and then it produces a Moire pattern. So Moire pattern has a different periodicity. You see this I have taken here and enlarged. The periodic structure is now much larger. You can play with things like printouts of something on transparency and rotate them. You can see this. So if the periodicity is large, A is large, so that effectively more number of lambdas are eligible for U scattering. So the Umklapp scattering increases, thermal transport decreases, and this is what we found by taking graphene sheets and rotating them, increasing the Umklapp scattering and decreasing the thermal conductivity just by twisting the layers. And in 2D materials, for example, you have a single layer of material, it interacts strongly with the bottom layer. The phonons of the bottom layer can strongly scatter the phonons of the material, and that can lead to a lot of decrease in the thermal conductivity. So just placing a material on two different substrates, the heat transport can be 4 times faster, 4 times slower. I think I'll stop here because I have also, it's time. So yeah, that's all.
Swayam Prabha. Digital India. Educated India.